Hello everyone, you're on the DP Labs channel. My name is Ivan, and today I'll answer some questions that subscribers asked under the previous video. This membrane won't be afraid of dust. In fact, not the membrane, but the stators of the capacitor. Actually, dust will get in there, but it's not really a big deal. Why? Because the stators themselves are insulated, meaning the insulation can withstand the voltage even with direct contact. So we have a positive potential. The membrane has a positive potential, and the stator itself is at neutral potential. And even if the membrane comes very close to the stator, there won't be any breakdown. The same goes for humidity. So if, let's say, in the mounting areas where the insulator separates the membrane from the stator, even if some kind of liquid gets in, it won't lead to anything negative or harmful. Because again, the stators are well insulated. How do these speakers handle water, dust, and temperature fluctuations? I partially answered this question in the previous response. Temperature fluctuations have absolutely no effect, none at all. Unless you plan to heat them with a hairdryer at 100 or 150 degrees, they'll be just fine. Does the membrane weaken over time? No, it doesn't weaken. Lavsan itself, or PET, to put it simply in Russian, is a polymer that is very resistant to mechanical stress. So basically, when I stretch the membrane with a certain force during manufacturing, that tension is maintained for many years. It doesn't weaken, so there's no need to worry. The question of the lifespan of a Lavsan membrane. Yes, and with a coating as well. How many hours are there in a day of years? Well, partly that too. This question has already been answered. The lifespan of a Lavsan membrane is quite long. As for the coating, yes, that's actually a good question. How many hours are there in a day of years? Different coatings are used on the membrane surface. Some people use only a conductive coating in the form of vapor-deposited aluminum, although that's not entirely correct. We use a high-resistance coating. Moreover, this formula was developed over a long period and has stood the test of time. I have several panels that were made 5 years ago and they still work absolutely perfectly fine. The conductivity of our coating does not change with variations in air humidity, so there's no need to worry about that either. And physically it adheres well to the surface. That's why, as I said, there are sound emitters that are 5 years old and haven't degraded at all. Here's another question. Do you need to calibrate it constantly? Do you need to calibrate such a speaker? No, there's no need to calibrate it. It receives its characteristics during manufacturing, so there's no need to calibrate it. As long as everything is fine with it mechanically, as long as you don't bend it over your knee, everything will be fine. Can two membranes operate using beat frequencies, for example, at 30 kHz with modulation at audible frequencies? Obviously, we're not talking about high-quality music playback, but about directional delivery, for example, of speech. Well, I haven't really looked into that direction, although I have conducted such experiments, if I'm not mistaken, on YouTube. There were videos where a person demonstrated an array of ultrasonic emitters, which are directional by themselves, and there is some modulation of this high frequency signal, which due to certain nonlinearity leads to, in the air medium, sounds in the audible range arise. A person experiences distinct sound sensations in their ear, which can be quite noticeable. I tried to do this with electrostatics, but honestly, I wasn't satisfied with the result I achieved. Not at all. That is, the effect is very weak. Most likely, those piezoceramic sound emitters that were used in those videos, if we're talking about the same thing, apparently had much greater power, and the effect there would be much more pronounced. And the second point is that indeed, there's no question of any high-quality sound reproduction, because there are quite strong nonlinear distortions, which perhaps could be compensated for somehow, but I didn't set out to do that since there was no need. And why would you need a standard audio amplifier for electrostatics? Isn't it possible to generate high voltage using a PWM converter controlled by a sound processor? Well, yes, on the one hand you can, and I even conducted such experiments myself. One of the first amplifiers, the direct drive, which is high voltage, actually worked on the principle of pulse width modulation. More precisely, it wasn't pulse width modulation, but something more complex. It used what is called multi-bit delta sigma modulation at a carrier frequency of 192 kilohertz. That's the way digital amplifiers are produced by some chip manufacturers, and the result I obtained was, let's say, quite promising in terms of efficiency. So yes, this amplifier does not heat up, but there are still major questions regarding its linearity and also its sound quality. If we're working with low voltages, for example, voltages in the range of tens or up to 100 volts, then everything will work just fine. But when the voltage is several kilovolts, the parasitic parameters of both the PCB and the conductors have a significant impact. That means you need to pay close attention to proper PCB layout so that, so to speak, the switch is open correctly. The amplitude is very high. It's quite possible that such an implementation might be made, but so far I haven't managed to pull it off. They tried to control the directivity pattern and the spatial frequency phase characteristics by zoning the polarizing potential. Here's an idea for you. In theory, you could tune the emitter to the room in a way that no other system with similar tuning capabilities can do today. Here, this particular question can actually be interpreted in several different ways. It's not phrased all that clearly. If you're talking about a situation involving a large number of so-called phased array emitters, that is, when we have an array made up of a large number of identical sound emitters, and we introduce certain specific delays into their signals, the behavior can become quite interesting. In this way, we create the specific directivity pattern we need, just like in phased antenna arrays. I've thought about this topic, and, well, this system is actually quite complex to implement, even aside from the physical aspect. The principle is clear. Here the main issue is more about computational power and the cost of such a system, because for each sound emitter of this kind, or for each segment of such a sound emitter, you need a separate amplifier for the matrix to work. And in addition, each individual amplifier will require its own DSP processor, which would be able to create the necessary directivity pattern on the fly with different apparent sound sources and so on. So physically it's doable, but the question is how financially justified it is. In other words, is this more of a utopian idealistic project? Although I have had such thoughts, I have pondered this topic before. What if, when mounting the stator, you leave a gap so as not to affect the membrane at the edges, thereby avoiding resonance between the center and the edges? So to speak, to create a suspension cushion, essentially, in fact, this principle is partially implemented in my design as well. That's how it works. So, as I understand it, the person is asking about something I talked about before. In the video, I mentioned that a membrane fixed at the edges has a pronounced resonance because the wave reflects off the edges. In other words, it's not fixed in the center, only at the edges. And so it reflects. If you approach this issue head-on, here's the solution. That is, let's say our stators are, for example, relatively small, but the membrane is fixed much farther away. Yes, so the force is applied only to the central part. So it's just bulky and, physically speaking, well, a questionable design. For example, in those panels where an acoustic lens is used to widen the directivity pattern, this principle is partially implemented, but it's done a bit differently. The thing is, the permeability of this acoustic lens, as you might expect, actually changes with, well, that is, in the center the permeability is at its maximum, while at the edges the permeability is much lower. In fact, this lens is calculated according to a Gaussian distribution, meaning there's a maximum in the center that tapers off toward the edges. At the edges, the membrane is much more damped by this lens, and this also, in a way, has a rather positive effect on the sound. But this isn't, what is this anyway? The train really seems to like this, you know. So in part, this principle is implemented in my design to some extent, although not exactly as it was proposed here. Although overall, of course, it would be possible to add some damping inserts at the edges of the membrane. But again, the question is how to glue them on so that they don't rustle or rattle, because even the slightest mechanical defects lead to noticeable audible sound distortions. Why not use a tube amplifier? After all, before the output transformer, the output there is high voltage. And it wasn't just one person who wrote this, several people asked the same question. Yes, you can use it, an amplifier. Some people use push-pull amplifiers which have two tubes at the output. And basically they connect the stators of the sound emitter to these out-of-phase tubes. It will work, but honestly, tubes are already considered a thing of the past. Sorry, because they get hot and they really do not offer any real advantages over transistors. I mean, you can waste several dozen watts just on heating the filaments, and people have actually done that before, but I'm personally not interested in that approach because transistors handle this much better, so why not just use them? Tell me, for low frequencies. Is the amplitude of movement between the grids sufficient? More precisely, what membrane excursion is possible with electrostatics to achieve frequencies below 90 Hz? Or does the system's efficiency decrease as the gap increases? The system's efficiency does not decrease as the gap increases. Look, we could make an electrostatic speaker with a distance of 1 centimeter plus 1 centimeter, that's 10 millimeters each. And the efficiency of this system would be exactly the same as with 1 millimeter plus 1 millimeter. But this system would require a much higher voltage amplitude. That is, we would essentially be supplying the same amount of power to the panel. But even in my own system, I typically use gaps of 1.5 plus 1.5 millimeters. In some cases, I tried 2 plus 2 millimeters, but 2 plus 2 millimeters is already too much. So accordingly, it turns out that even just 1.5 plus another 1.5 millimeters is absolutely necessary in order to get a normal, clean and loud sound. You really need several kilovolts of voltage, and if we increase this distance to, say, 10 millimeters, we would then need, well, about 100 kilovolts, and accordingly, the price of such amplifiers would also increase. And I don't even want to think about that because honestly, I don't want to go mentally above 15 kilowatts. Because at that point, everything starts to... At 10 kilovolts, any conductor that has a 10 kilovolt potential will already start to produce ozone. A corona discharge appears very easily. So this means increased requirements for insulation. Below 10 kilovolts, you can still, so to speak, turn a blind eye to some things. Here the issue is different. Roughly speaking, the optimal gap between the stators as well as the distance between the membrane and the stator needs to be carefully chosen based on the specific requirements of the task. That is, the lower the required frequency, the larger the gap between the stators needs to be. But accordingly, the higher the voltage amplitude will need to be. Accordingly, if we are working in the mid to high frequency range, or say in the mid-bass, mid-range, or treble, then in principle you can even reduce the gap to 1 millimeter. And this, on the contrary, will increase the volume and reduce the required output voltage of the amplifier, and accordingly everything will be fine, probably. With that, we say goodbye to you. Until next time, please like and subscribe. Like, comment, and subscribe in the comments. Maybe I'll keep answering in the future. Bye for now. Oh, I forgot to answer. What kind of watch are you wearing? Is it an Apple Watch? Yes, I have an Apple Watch, but seriously, in that video, those were some watches from AliExpress. They are open source watches on M32. I think the cool thing about them is that they have an e-ink display, which I really liked. Even though I ordered them and they've arrived, I haven't actually figured them out yet, just like that, but they're pretty cool.